Danna Gurari is an assistant professor at the University of Texas at Austin, where she directs the Image and Video Computing Group in the school, the iSchool, basically. She did her undergrad work at Washington University in St. Louis and her PhD at Boston University, but in between there, she worked here in the Front Range at Raytheon and Boulder Imaging. So she actually knows about Colorado, which is why she's back. Her research interests span computer vision, machine learning, human computation, crowdsourcing, human-computer interaction, accessibility, and biomedical image analysis. And she's won a stack of awards at conferences in areas ranging from the big ones in ChI and computer vision, and also more specialized ones like medical image computing. And she's going to talk to us today about some of that work. Thank you.
It's a pleasure. Thank you so much for having me. Thank you all so much for being here. My name is Danna Gurari, and I look forward to talking to you about my team's work on designing computer vision algorithms to support real users and recognize multiple perspectives. So in this talk, I'm going to start with a little bit of background on computer vision, then go into the past research and future ideas. So diving in, computer vision is the field around making algorithms that see. Today, you'll see computer vision algorithms in things like self-driving cars, vehicles on Mars, guided surgery, visual assistance for people who are blind, as well as to more efficiently log on to your personal devices by just snapping a picture of your face. And so I wanted to talk a little bit about how did we get to where we are today. The basic ingredients are emulating the ingredients of sight, the brain and the eyes. So if we take a trip back in time, 1945, time of World War II, you have the first computer that emerged. Time of World War II, we needed to put out faster computation to help in that time. First programmers were women who were not off at war. Fast forward to 1957, the first digital image. This is it. It's of a 3-month-old son of the person who took the picture. What is an image? It's a grid of numbers in the case of a grayscale image. Okay? That's what a computer sees. What we see is a mapping to various colors. Think paint by the number. Fast forward to 1966, out of MIT comes the paper, the Summer Vision Project. The dream? Solve vision in one summer.
By an undergraduate.
Yes. Here I am today. So in the scheme of, I believe there's a lot of people here doing artificial intelligence, thinking about how do we make machines that do intelligent things in different ways. Computer vision sits as a subset, thinking about machines that see. While hopefully you see computer vision has been around for a long time, the research community didn't bounce on that until between 1980 and 1990. The most important conferences in our community include CVPR, followed by 1987 ICCV, followed by 1990 ECCV. So if you're curious about what are the premier places, that's the premier places to be publishing your work. Many other conferences also exist with variants on various applications and more. If you look over the past 15 years-ish, from 2006 to 2019, at the number of attendees at CVPR, this is an example of what's going on at all of the computer vision conferences. What you're going to see is rapid growth. So last year when I was there was 9,400 attendees. They sold out. You couldn't register if you didn't get registered in time. Why the rapid community growth? Over the past 10 years, we see that computer vision can work in practice. People see that, they want to get involved, and so we see that there's a huge rise of people who are interested in joining the community. The typical computer vision pipeline today consists of the following 3 steps. First, create a large data set. Then, design an algorithm, train it and evaluate it. Finally, deploy that algorithm in some real system that goes out to end users. This idea, if you look at the first 2 steps, is analogous to how you might teach a child to recognize whether or not an image shows a person. Beforehand, you might show that person that child many examples of people in different shapes, configurations, sizes, and so on, so that when they see a novel case, they can say, yes, there's a person, or no, there's not. That's the idea of what's going on with algorithms today. So just to pinpoint where my specialty lies, I've created 2 courses that I have taught now for 3 semesters each on addressing these 2 steps. First is called Crowdsourcing for Computer Vision. All my slides are publicly available on my website if you ever want to know what I teach on this, as well as a class on Introduction to Machine Learning. Okay. So now I want to talk about my research and what we're addressing. And in doing that, I wanted to start with the inspiration for me to pursue a career in research. I did work here in Colorado. I worked at a place called Boulder Imaging. And at the time, we developed cutting-edge video recording systems. We were recording massive amounts of data for many customers, including NASA, Lexmark, all over the world. And what we were doing is we were fueling the data that would be used for analytics. In parallel, I was supported to come up to seminars just like this at the CS department, which I did do. I thought it was so cool that I decided to move away from Colorado and get a PhD. Here I am. Okay, so thank you for inviting me. It's a pleasure to do a full circle and be back here and share about the research that I've been doing. In my team's research, we largely focus on 3 key problems. The first is that there's a data set mismatch for real users' needs. The second is that there's also often an algorithm mismatch for real users' data. And the third is that algorithms return one-size-fits-all responses. And so the goal for my team is largely thinking about how do you design computer vision algorithms that support real users and recognize multiple perspectives. So I would like to spend the rest of my talk on these ideas. I will go over next the research questions that I'm going to address, how to empower the community to design algorithms that match real users' needs. Next, how to design human-machine partnerships to efficiently produce accurate results. How can algorithms anticipate when and why crowd responses will differ? And finally, how can algorithms recognize the multiple possible solutions for a task? So those first 2 questions are really focusing on how do we support real users. The next 2 is how do we think about designing future algorithms that can embed multiple perspectives in them. So diving into the first one, the motivation again for this one is about the dataset mismatch from real users' needs to the datasets we use in practice. This work that I'm going to discuss has been funded largely by Microsoft and Amazon. The task I'm going to talk about is describing an image. So given an image like this, one thing you might want to do is describe it with a caption such as, a bunch of small light brown mushrooms in a green field. Alternatively, you might want to answer a question about that image, such as, is it edible or poisonous? And get back an answer, in this case, poisonous. These 2 tasks are very important for real users today. Already, people who are blind have been using these systems to take a picture, optionally record a spoken question, have that sent off to remote humans, whether that's employees at a company or crowd workers, who will in turn provide a caption or an answer to that question. This idea has been around now for about a decade, starting with VizWiz, which Tom Ye, wherever he is, was part of creating. And there's been many other companies and products that have emerged over time since then to do exactly this. While the computer vision community has put out data sets to try to develop progress in addressing these tasks, there again is a mismatch. I show 3 examples on the top row from existing state-of-art data sets, as well as 3 visual questions from real users. The mismatch stems from how the data was collected in part. The picture in question were collected independently from prior work. Pictures were scraped from the internet, often from Flickr. Questions were contrived. So typically you would show a crowd worker an image and say, think of a question that would stump a robot. For real users, it's going to be the same user who both took the picture and asked the question, and the data reflects real users' interests, such as learning the flavor of the food, learning the temperature of the thermostat, as well as whether or not their shoes match. So given that, we decided to embark on creating a big labeled data set originating from real users. From a previous app that had been used between 2011 and 2015, over 11,000 people had submitted over 72,000 requests to this app. Of those, 60% of the data, the users agreed to share their data for 62% of those requests. So that is the foundation of this body of work. In making the data set, again, this data comes from real users. We had a lot of extra steps that we had to do to make sure that we could publicly share that. This included anonymizing the data by transcribing questions to remove voices, resaving images to remove metadata such as people's locations, filtering out any sort of personally identifiable information. There aren't taxonomies yet around what is private information, what is personally identifiable information. We took a stab at it, we went through all images numerous times, removed what we thought was deemed that way, including people's faces, their medication information, as well as their mail, which can show their address, as well as other important information. Bless you. Finally, took the remaining data, had that sent off to the crowd to label it with high-quality captions, as well as answers. The result is 2 data sets. For visual question answering, we have 10 answers for every visual question. For image captioning, we have 5 captions for every image. For the community, this is the first data set where real users requested image captions and answers to their visual questions to support their real daily needs. Most commonly, people are talking about everyday objects. So if you look at a word map of what are the most common words that are used to describe their images, often we have things like bottles, packages, tables, counters, boxes, and computers. What kinds of questions are people interested in? Yes.
So I'm wondering, you have the original answers from back when these questions were first asked?
We did. We threw them out. They weren't sufficient quality, and it was sporadic how many answers you had. At the time, the app collected, on average, 3 answers per visual question, but it could range from none to 6.
Yeah, it'd be especially interesting if you have feedback from the people whether the answers
Yes.
worked for them or not.
Yes. Hold on to that thought. Hopefully I'll get to that a little bit more, but I think that that's a very important direction for continued future work. Oh yeah, and just on that comment, if you have questions, please feel free to interrupt throughout the talk. So what kind of information were people asking about when they had a question? Often they asked, what is this? From a language perspective, this data set is also very interesting because many people use very conversational language. Unlike prior data sets, they say, please, hi, okay, in providing questions. And so if you're interested, all this data set is live. You can actually search through it. Here is just a visualization where I'm going to show a tidbit of expanding out to 50 images from the entire data set. You can click on any one of those images to zoom in and see the question, the collected captions, as well as the answers. There's also extra metadata on additional labeling we did that you can use to search and learn more about the interests of this population. Cool. We have a new data set. The goal is to get people in machine learning and AI and computer vision more generally to think about this problem. So we next wanted to figure out how hard is this data set for the community. So in doing that, standard pipeline is you have your data, split that data into a training set and a test set. Train that algorithm on the training set, take that trained algorithm, and apply it to your test data. So an example like this, predict an answer, see if it matches, it does. See if it doesn't, tally over the many, and you can come up with some performance metric. So we did this. We did this for pre-trained state-of-art algorithms. Took state-of-art algorithms, fed it the most popular computer vision data set before this data set. We evaluated across many metrics. I show just a subset here. The point is algorithms perform very poorly. Okay? Did a second scenario. Maybe it wasn't the problem the algorithms. Maybe it was the data. So what happens if you take these same algorithmic architectures and you feed it data taken by people who are blind? Same story, you get a bit of a boost, but algorithms perform poorly. Let's try one more thing. This is a small data set for machine learning. What if we use the combination of the old and the new data set? Try that. In a nutshell, algorithms perform poorly. Great for publishing. So what makes this hard? We've tried to detangle that. This data matters for a real use case. It's fun for publishing, but it also, if solved, could change people's lives. This data set is challenging for algorithms for many reasons, including that many images are low quality. Many contain text. That is not the case for other data sets that are out there. And they contain novel concepts. So many images contain things like currencies, CAPTCHAs. And it turns out a lot of them are taking pictures of images with Kellogg branded items. So we put out a data set. Goal, again, is to help real users. We wanted to engage a community. So that's what we did. To accelerate progress, we shared our data sets publicly. Others are also sharing our data set. You can also download it in academic torrents in Kaggle, and Facebook put out a new language and vision platform where it's included there as well. To track progress, we also provide a public evaluation server with leaderboard. Currently, people across the world are competing, and they can see where they stand on the international ranking in terms of their algorithm's performance. We also organize events to foster a community and celebrate progress. Our first event was in 2018. We will have another one in 2020 at CVPR this summer. And for those of you, and so in terms of impact, we have a growing community. We've had people write Medium articles, MIT Technology Reviews. People are writing articles about how they're winning or in the top 3 on this challenge and tweeting about it in the data set. And so if you're interested or you want to put a student on this, I invite you to join. Here's how it works. As before, I said, we split each data set into a training set and a test set with the target responses for the test set hidden from you all. Design an algorithm and submit its predictions on the test set by May 15th. The top teams will win $10,000 in cloud computing credit. If you're interested, feel free to ask me questions, both after this talk, and I believe we have a colloquium afterwards. Yes?
So the questions that people are asking, are they very objective questions, or are they kind of subjective labels, or like subjective answers?
Great question. So they're not fact-based, they're not just objective. There are many variants. The third part of my talk is going to talk about what are those kinds of differences that we see, what kinds of questions, what kinds of answers are being elicited.
Awesome.
Great question. Great. Okay, so at this point, I want to shift to discussing how to design human-machine partnerships to efficiently produce accurate results. In this case, the motivation is that there's an algorithm mismatch for real users' data. This work has received lots of funding from the Silicon Valley Community Foundation. Priscilla Chan and Mark Zuckerberg are trying to spend 95% of their funds before they die. Part of that is to be able to figure out how to prevent and treat many diseases. And they funded our project in helping them understand how cells, to build tools to analyze cells in the human body. And so this work is sponsored in part by them. And the task for this work is thinking about object segmentation. So while the motivation and funding for this work comes from biomedical images, this task matters all across the board for biomedical images, medical images, and everyday images. For many tasks, including to do things like object classification, object tracking, image retrieval, and rotoscoping, which think Hollywood, where you create a really cool background when someone's not actually at that cool background. A typical user experience looks like this. You have a user interface with a bunch of algorithms. Let's call those 1 to 7. Often these algorithms can be interactive, where a person will click some initial region, doesn't take a lot of human effort, and then run an algorithm. And sometimes that algorithm does terribly. So at that point, you might run another algorithm. And in the second case, you'll find it works beautifully. Okay? So it takes a lot of time for a user to figure out which tool to use when. So key observation, algorithm performance is inconsistent. In some cases, algorithms do well. In other cases, they don't do well. So the idea of this work is to involve humans when they are needed most, when algorithms are failing. So the foundation of this work is based on a method that can predict the quality of an object segmentation. So given an image with a ground truth, which is what we want the algorithm to produce, we want the algorithm, the quality prediction mechanism, to be able to, with only seeing the image and algorithm-drawn segmentations, decide, is it really good, is it bad, or is it somewhere in between? So when I talk about quality, there are many metrics we could use. In this case, I'm going to talk about the Jaccard Index, just to put us on the same page. We'll use this as a toy example. You have your ground truth, you have your algorithm result, intersection over union, overlay, look at the pixels in dark green, which is the intersection, 19 are in common. Look at all the pixels together, that's 27. The performance for this algorithm-generated result would be 70%. And so that's what we're talking about for quality. So the key ingredients for putting this together was we got a data set. We got over 10,000 images from 4 data sets. For each image, we applied 14 different algorithms. We also, because we wanted high-quality results in a similar amount to the failure cases, developed 3 different segmentations that come from the ground truth. Use that to train 2 prediction models, one for our 2016 paper, one for our 2019 paper, using linear regression model and regression tree ensemble. We did use CNN-based methods. They did terrible. So for those of you who are curious, I'm not showing these results because they just don't do as well. And I'm happy to talk offline about that. For each training instance, we evaluate the segmentation similarity to the ground truth. We compute 9 features that describe the binary segmentation mask, as well as 3 CNN features that describe the image properties. So for our data, you'll have all the segmentation examples, which are each either training or evaluation examples. You'll have the score for each, the 9 binary mask features, and then the rest of the features come to describe the image. After training this method, what you get is, as input, an image with a segmentation algorithm. It produces a segmentation. That segmentation, an image gets passed to the feature extraction module. The features are passed on to the prediction module, and out comes a quality score. How does this do in practice? We explored, again, with 4 data sets. We evaluated across 2 different metrics, the correlation coefficient and the mean absolute error. I'm showing our results from our top performing method, the random forest method, as well as what was the previous state-of-art method. And without going into the details of the numbers, what you want to see is higher CC scores and lower MAE scores, and our method consistently outperformed the previous state-of-art method. What is really cool, in my opinion, about this is what I'm showing is results from cross-data set analysis. So train on the 3 data sets not shown in red, which are grayscale images and color everyday images. Take that, put it on the test examples, which is a data set on biological information. And what you get is very good results where the algorithms can generalize what's learned from everyday images to biomedical images. With that in place, we turn back to thinking about the user. How do we help the user be more efficient in collecting segmentations? So this is the pipeline, diving through the steps. The first step is to pair each image with a segmentation. To do that, we first took each image, produced 14 computer-drawn options, used our prediction module to predict the quality of each one, and then we kept the best one, shown highlighted in red for each image. Next, we applied an algorithm to refine each chosen segmentation per image. Okay, so we use that as a coarse initialization. Given an image of ground truth, let's just go through what that looks like. We could have an input that comes from our predicted input, looks pretty good, refine it, get a little bit more detail. In contrast, you might get a chance output, which is randomly choose from those 14 candidate algorithms, one option, and then make an output. Or another standard is to use a rectangle and get an output.
Excuse me.
Yes?
Could you explain what the 14 algorithms are?
Oh, yeah. So their CPMC is constrained, I forget what it stands for, but it's an object region proposal method. So that's one which it looks at an image and it tries to find like what are salient regions. We also use what's called Otsu Thresholding, which is an image-based thresholding method. Hoff transform. I have to remember what else we did. I don't remember all of them, truthfully, but it's a whole span of, so how did we choose them? Maybe I'll answer that without going to it. So we were working across two communities. We were working in the biological community, and we were working with the computer vision community. And while in theory we would think that because we're all working with images, we might care about the same tools, that's actually not what happens. The communities have some separation. So we took the methods that are being actively used from the biological community, which are actually really old algorithms. They work very well. Hoff transform is my favorite. It works just really well in practice. And then we took the state-of-art methods from the computer vision community, which are these region proposal methods. So these sophisticated methods that put out, here's definitely objects in the image. And that's how we came up with our collection of methods. So I hope that answers your question.
How many were from the biology side and how many from the computer vision side?
Good question. I think it was like half and half, but I don't remember. That's a good question. Yeah. And so, altogether, you can see that things like a rectangle can work somewhat well in practice. Chance output just does pretty terribly overall, but in our method, it does very well. We did quantify that. We found on average that intelligently choosing from 14 options leads to a 15% improvement in the resulting segmentations over existing baselines for 3 refinement tools. Okay? So at that point, we took the result from the refinement algorithm, predicted the quality of the resulting segmentation per image, and we were able to pair each image with a segmentation. Next step is we rank the images from the cases where we believe we have the highest quality computer-generated results to the lowest quality. At that point, allocate the available human budget to those instances where the predicted quality is the lowest quality. In terms of results, we took our approach and compared it to the state of art at that time. State of art at that time took an image, and it involved humans for every image using one of 3 options. It predicted whether to provide a fine-grained result, so give all the details, which can take a human about 54 seconds, or have the human draw what's shown in green, the square, takes about 7 seconds, or have the human create a course outline, which takes about 20 seconds. So that was very innovative when it came out. Our work we compared to that. And here's the results. What you see on your left side is where computers generated all the results. At the right side is where a human created all the results. And in between is where you have some sort of mix of human effort. Key points I want to make is that our system works even when a budget is not available for every image. That's one advantage. Another is that intelligently allocating human effort typically eliminates 5.2 to 11.5 seconds of annotation effort per image compared to what had been the state-of-art method within that range. So, yeah. And so in this case, you could get about 40%, with 40% of human involvement, you can get the same quality level at about 20% human involvement. So to summarize this component, this work showed that you can intelligently involve humans where they are needed the most. So now I'm going to shift to the question about subjectivity earlier, and exploring how can algorithms anticipate when and why crowd responses will differ. And so this work looks at addressing that algorithms return one-size-fits-all responses. This work has been sponsored by NSF and exploring exactly the question that I'm about to present to you. And so the task that I'll talk about, we've done this for a couple of tasks, but I'll just focus on visual question answering, which is given a question about an image, return an answer. Key observation, again, we collect multiple results for each task from different people, is that sometimes crowd responses can match. When that's the case, collecting redundant answers compromises efficiency. It's a waste of time and money. Other times, crowd responses can differ. In that case, collecting multiple answers captures diversity, shows the range of plausible answers. So if we really distill that down, redundancy can be wasteful or valuable. So, key idea for this work is to predict whether crowd responses will differ. So we created a module that did that, takes the visual questions, and it predicts answers match when it believes that's the case, and predicts answers differ when it believes it's not the case. You can take those predictions to then decide when to collect one answer, because that should be enough, versus many answers when it's not enough. Compared to the status quo application at the time for collecting answers, what we found was using this approach could save 23% of the cost and time with no loss to answer diversity for over 120,000 visual questions. This led to a follow-up question. That's great, we can be more efficient, but we still have crowd responses differing. And we wanted to know why, and we wanted a machine to be able to then tell a user why. So with that, we embarked on the idea of designing a data set and algorithm for recognizing why crowd responses will differ. So we made a data set. We labeled almost 45,000 visual questions from 2 different VQA data sets with 9 different reasons for each visual question of whether or not those reasons are valid. And then we provided an algorithm that, given an image and question, predicts what, if any, of those reasons are reasons that crowd responses will differ. So looking at what taxonomy did we choose, that was informed by our prior work and our analysis of the data. And we came up with a taxonomy that includes subjectivity. So could the floor use a mopping? Some people think yes, some people thought no. We also came up with, often there could be synonyms. So how are the water conditions? You look at the answers and people say calm, lucid, various similar meanings. Other times the visual question was ambiguous. Which side of the room is the toilet on? You'll see from crowd workers, the middle of the room, the left of the room, and the right of the room. Other times it's just spam. So you couldn't have predicted it. Some person showed up and gave a spurious answer, and it's just garbage. That's very rare. It's less than 1% of the time, and it's one of the most, a lot of attention is given to spam in my experience in this data set. It's the least important reason. Other times the answer was just missing. You can't find evidence of the answer in that image. Visual question could be super difficult. How many sheep are there? Low quality images makes it a little bit harder for people to come to agreement. You sometimes just have an invalid question. I just wanted to say thank you for your assistance. People don't know how to respond. And then detail level, people offered, especially when you have text present in that image, people offered different amounts of detail and how much they copied over from the image to provide as an answer. So what book is this? Some people just said the title, others gave the subtext as well. Okay, so we came up with that taxonomy, labeled all our data sets. This taxonomy, for us, we found it really interesting because it helps think about future system designs. One thing you can think about is that you could, if you knew, given a visual question, whether the image was low quality or there's an invalid question or the answer is missing, you could tell the user, retake an image or re-ask the question. The alternative, if you have human-based services, is they can wait up to 2 or 3 minutes to learn that they need to rephrase their visual question. Okay. For system designers, there's a number of things they can do. I didn't put one of them up, but for Bo, we talked about output agreement. How do you aggregate different responses? There's a pool of algorithms about that. You could certainly help system designers figure out which method to use to aggregate different responses. You could also figure out when to recruit more costly experts to come and do the task. Okay. So that was a taxonomy we came up with. In terms of our algorithm, hopefully it becomes clear it's not obvious how to design an algorithm to do this, because as a human, you need the image, you need the question, and you need to see the answers for some of those cases. But at test time, all you have is the image and the question. So the key idea of this was to take advantage of the fact that we believe that algorithms are currently implicitly learning when there might be multiple answers in them when they predict an answer. So we have algorithms today that, given an image and a question, will predict an answer. Some of those algorithms will give you a distribution of their confidence. I'm 60% sure it's yes, I'm 40% sure it's no. Some confidence distribution. And so the idea is maybe computers are getting confused when it realizes there should be more than one answer. And so that's what we did in designing this algorithm. We took advantage of that intuition. We designed a neural network-based algorithm that takes in the image and the question, passes that through an answer prediction module, then has that image, the question, and the answer predicted, the distribution, go to another module, which then flags what are the reasons for why crowd responses would differ. Okay. So this was a novel problem for the community. So we didn't have any methods to compete against. The question was, does this work? We found yes, algorithms can anticipate why crowd responses will differ better than random guessing by a long shot. And if you look at related methods that you might try to adapt for this purpose, you find this kind of system even works better than those. These problems matter for real end users. So as before, we have shared the data set publicly, and we have created a public evaluation server with leaderboard to try to get a whole community to be working around this problem. Okay, any questions before I go into the last piece of prior work? Cool. So last one I want to talk about is how can algorithms recognize the multiple possible solutions for a task? This work has largely sat in collaboration with Adobe. And we're again addressing that algorithms return one-size-fits-all responses. For this task, it's thinking about what's called image in painting. So given an image with the region in red, we want to remove that and insert something that's plausibly realistic, but different. There are many applications for this, including personal photo editing, advertising, landscape architecture, augmented reality, interior design, as well as privacy obfuscation, which is something I care a lot about. Status quo. Today, if you want to do this, many people do it this way. They would take an image, cut out their little hole, go search some database to find their beautiful image that they love, find it, put that in the image, apply an algorithm such as patch match that synthesizes some background and get a result, and do that over and over and over until they find what they're interested in. Okay. In 2018, a team said, let's do a little bit better than this, and they proposed an algorithm that can take the image with the region and a category, and then look through that database and output what might be plausible things to put in that hole. Our novel idea is a problem we called unconstrained foreground object search, or UFO search. Take in an image with the region, search a database, and we want to figure out what are all the compatible objects across all categories. So in this work, the goal is to go beyond what we said in the previous study, which is just recognizing when and why crowd responses will differ, but start to identify the variety of plausible results. Intuitively, if you look at the top image, you'll see it looks like an umpire. You might not be able to see it. There's a strong light, but there's an umpire. There's someone that appears to be running over there. It seems like only a catcher in a baseball game might fit there. In contrast, for the bottom image, you have a plate on a table. Perhaps any kind of food could fit in that context. So figuring out what is appropriate for each context is the challenging thing for an algorithm. The solution put both the background image with the hole in the same latent space as all the objects that are candidates. Putting those together, then find compatible objects, and then with post-processing, you can then come up with the alternatives. So I'm not going to go into how to train this. I'm happy to answer questions. I have a slide where I'm happy to go into details, but I thought with the fourth topic, maybe I should lighten up on the details. But what happens is, computed offline, we come up with a way to map all the objects where we put similar objects closer in the search space, dissimilar objects further away in the search space. We also trained beforehand an algorithm that is able to encode that image with a hole into the same search space such that it will land close to the objects it's compatible with and far away from those it's not. And then return compatibility in order of ranking of what's most to least compatible. Hitting on what I think is really exciting about this work, this system is able to learn when to return no diversity. So it's able to learn when to only return one category of catchers. It's also able to learn when to return a diversity of options. In the bottom case, many different kinds of food. Okay? So it's starting to learn about how to use the context to figure out what's appropriate within that context.
Is that because
Yes.
the label is limited to certain choices?
When you say the label's limited to certain choices, can you tell me what you mean by label?
So, I mean, the no diversity versus diversity, model is able to learn which cases it can, the model can pick no diversity versus diversity. Is it because the people label it?
We have no. So we have, it's a great question. So a challenge with this is when you start, you have one image with one ground truth. What do I mean by one ground truth? You have that really original image with only one object that you know could have lived there. You don't have anything else. And so the trick that I didn't go to in talking about the details is part of what we did is we figured out how to create a bunch of examples that are appropriate to fit within this context. So part of the novelty of this work is figuring out how to artificially create training data. No human labeling, how to do all that automatically. And so that's one aspect of the novelty, and the other aspect is in the algorithm design. But when you start, you have, for each image, you have just one labeled truth, which is the content that was originally there before you removed
So
it.
you're creating some true data distribution that's possible and then make it all generate from there.
I wouldn't call it true. We're making an approximation, and it works well in practice from our experience. We did crowdsourcing studies to get realism. We did quantitative studies as well as qualitative studies, and what we found is this method can do a reasonably good job, where crowd workers are like, yeah, that looks like a realistic object to put in that image.
Also capture some kind of, how to call it, the size, some, concept of size, like the scaling of that object kind of matches to.
Yes. Great question. That is one of the deficiencies of this algorithm. So future work, if you're interested in building off of this, would be figuring out how do you deal with the scale. Geometry is another issue we didn't deal with. So it's learning what's appropriate for the context, but it's not learning how to perfectly fit within the image necessarily. Okay? So there's a lot of aspects that's really hard to do the whole pipeline perfectly.
What makes it difficult to make that scale with the model to run that scale?
I mean, partially, that's a good question. So what makes it difficult? If you have unlimited data, everything's trivial for right? But you don't, so that's part of it. If you have an algorithm that has embedded within it a module, so we build an end-to-end system, so you need to embed some sort of module that would deal with the scale, but now you need to make sure everything works and that scale module doesn't compromise on the performance of other things. So could you do it? Yes. Do I think it's important for you to work? Yes. Did we do it? No. So, yeah. I think in general, when you try to put together an end-to-end system, you'll find that choosing to prioritize one thing, such as diversity, it gets diluted when you try to put in other things you're trying to optimize as well. And the key is how do you do that seamlessly? Does that answer your question? Okay, great questions. Okay, I actually can't see a clock, so I don't know how I'm doing on time.
10 minutes.
10 minutes? Okay, great. So that's it for the past work that I wanted to share with you all. To summarize, this work was really looking at data sets that match real users' needs, designing systems that can efficiently involve humans to counteract algorithm mistakes, and also designing algorithms that can recognize and convey multiple perspectives. In terms of future work, still looking at that pipeline, the future work I'd like to talk about is data sets for analyzing private content, systems that, again, involve humans to counteract algorithm mistakes, but now in 3D, which is much more complicated, as well as context-aware algorithms. So to motivate the first problem, the first of these three future work projects, we did do some initial work that revealed that 12% of images taken by people who are blind show private content. Okay, so this is a real problem. Here you see examples of face. All the data, the original data is obscured. I will not show you any private information. So you'll see in red the circled out regions of what's obscured. It might even be hard if you had the original information to find it because these are, again, low quality images, right? But that's the issue, is how you deal with that. And of note, it's not just enough to flag whether or not they contain private information, because 20% of the time, people share private information intentionally as a trade-off to learn about the visual world. For example, they might want to know, is this pregnancy test positive or negative? What is the medicine in this pill bottle? Okay, yes?
So in the other 80%, they were asking about something else in the image? Or something?
The other 80% accidentally captured private information. So what does that mean for if you want to think about how do we deal with privacy? We want a system that can handle multiple things. And I'll get to that in a second. We did come up with a taxonomy. This is an open problem for how do you even come up with a taxonomy that really addresses what is private versus not. We're doing user studies to ask people who are blind to help us with that, and we'll have some responses by April on what do people who are blind at least think is private. But we in-house went through a process of figuring out some categories, and this is what we came up with. So if we think about this, the data really is complicated because we can have things that are private from the object standpoint, as well as it could be text and where that text is situated that makes it private, okay? And so in thinking about how do we deal with this real world problem, we want to develop algorithms that recognize, obfuscate, or answer questions about private information, okay? We do not want to ever share the private information. So this situates in a broader set of problems, which are long tail problems where you just don't have a lot of data examples. And I'll focus on the privacy. So where I'd like to go for future work is generating a data set that contains fake, realistic, private content so we can start to support these use cases. Hopefully some of you are like, whoa, that sounds terrifying. Yes, that's terrifying. We need to figure out what information is deemed private when, and we also I've contacted a lawyer already about thinking about what are the usage regulation guidelines that are needed to avert unintended dangerous uses and consequences. So very interdisciplinary work, but I think very practically important work. And technically it's very challenging because private information spans objects and text, and figuring out how to inpaint and all that, we are far from that. The results that I obfuscated with, hopefully, if you remember what they look like, they kind of look like garbage. That's the state of our algorithm. So we have a long ways to go, technically. Another future work is compensating for algorithms failures for 3D data. So 2 examples of thinking about 3D data. One is you have an image from a stack, lots of medical data looks like this. And so you might want to find regions, segment out regions, or find matching spots. The other is following in video data objects over time, such as these cells, being able to locate where they are, their shapes, all that metadata. Generally, if we can build tools that can do this analysis of 3D data, we could accelerate basic science research and medical discovery. I believe algorithms are far from being where we need, and we need to make something useful. And I think that what's interesting in that is creating the hybrid partnerships. And the key questions are figuring out when and why do algorithms fail? Not per algorithm, but starting to think about properties across different algorithms. And then how do you design crowdsourcing systems? When you're dealing with 3D data or a video, it would be tedious to show a human the entire video or the whole 3D stack and have them maneuver it. So there's some challenges in crowdsourcing. Also figuring out what kind of human involvement is an interesting aspect of this. And the last one is thinking about context-aware algorithms, and one use case is image captioning. So here's an image. If you ask today's state-of-art algorithms to describe that image, you will get from an algorithm something like a man and a woman sitting on a bench. We conducted a study with asking 28 people what kind of information they'd want in 7 different contexts. Some of you, I think, are familiar with the title. It came from Abigail Stengel, who was finished her PhD at CU Boulder and is now a postdoc in my group. And she helps us uncover what do people who are blind want in different contexts, in particular 7. Just to narrow it down to 3 of our findings. One is if you're in a social media feed, if the image was in a social media feed, you'd want the person's facial expressions, their body language, and their interaction with the environment. So the content in red. On a dating website, you would want to know the person's physical characteristics and the setting to learn about that person's interests. On a shopping website, let's assume it's clothes, all you care about is the clothes and the person's body type to know whether or not that model's body is similar to your body. And so the goal for this work is to develop algorithms that can move beyond one size fits all and really return the appropriate caption per context. This has a number of key challenges. One is, how do you efficiently crowdsource captions to ground content for each context? When I say ground, I mean put language to actual physical locations. So think the blue region, the red region, or the purple region. To efficiently do that with crowdsourcing is very difficult. That requires much innovation to think about how do we collect a large-scale data set if that's the way we go, maybe human-machine partnerships. The other is, how do you design new algorithmic frameworks that can simultaneously learn all the information across these contexts and also figure out when to fire with returning each kind in a human-like description. Okay. So that wraps up the future work. There are many people to acknowledge. I have had an amazing group of mentees. Their images are up in the upper right corner. In terms of the work, I've had many colleagues that have been very instrumental in the work that I've presented. There's also been many people who have contributed to the data set challenges that we have. It really takes a community to do a challenge, and we've been very fortunate about the people who have contributed. And then, of course, there's been thousands of crowd workers who have given tens of thousands of their hours to this work. We've also been very fortunate to get generous funding from NSF, Microsoft, Adobe, Amazon, Silicon Valley Community Foundation, as well as UT Good Systems. So with that, I very much welcome any questions. Thank you for your time.
We had a lot of questions in line, but I'm sure there's still time for a few more.
Okay. So, great talk. Thank you very much. On the subject of one size fits all, a lot of these approaches treat humans as interchangeable units where we know very little about them or what makes them different. And so I'm curious of your thoughts in these domains. What are we missing by taking that view of humans, or where are some opportunities where if we had a richer model of what humans were actually doing, that would make this work even better?
So I certainly think there's a lot of cues that tell you about what people's mindsets when they're responding. So if we think about the crowdsourcing environment, you have cues like how long did they take before they responded? How many times did they type and then delete? Like how contemplative were they? So you can certainly use behavioral mechanisms. I say that, but I also wonder how ethical that is. And so there are some questions about in crowdsourcing, how far can we go in collecting people's information without notifying them? But I think that's a valuable direction. I think fundamental cognitive science studies, I'm not gonna go there because it's just too far of a leap, but I'd love to collaborate with people who are there. But just, understanding how different perspectives can arise, and that can even just be in terms of how people have learned language. That can be culturally between cities, countries, states. In terms of, so that's on kind of the data collection side, but I also think we have a lot of studies to ask about what do users care about? Like maybe a user doesn't care if they're synonyms and they're all equally good, and we shouldn't deal with collecting redundant responses in that case. And so doing user studies on the end user aspect and really understanding what are these important problems. We've kind of come up with a taxonomy, but enriching our focus on what really matters to people. So that's some thoughts. Thanks for the question.
So given all the wonderful questions that were in line, we're kind of out of time, so maybe